to talk about the frequency response methods for analysis and design. And you'll see that using the frequency response, and I'll talk about that, we can determine things like again, the stability, the range of gain K for stability. We can also determine the relative stability, in other words, how stable it is, with some things that we can measure from these frequency response plots of magnitude and phase. We can measure what are called the gain margin and phase margin. Those are measures of how stable the system is. And the frequency response that we're talking about is based on the open loop transfer function when we replace S by J omega. Okay, so we would have G of J omega times H of J omega. Again, in design of control systems using the frequency response, what we're going to be doing is shaping or reshaping the Bode diagrams. These frequency response plots are called Bode diagrams. We're going to be shaping the Bode diagram of magnitude in order to satisfy the transient and steady state response specifications. Let's start out with a simple example and find the frequency response of the system, or at least find the expressions for magnitude and phase from which we can find the frequency response. So let's consider a liquid level control system. A liquid level control system. So what you have is a tank. And the tank here has an input, right? So an input here, you've got liquid coming in, okay, at the rate of U of T. So there's so many cubic, feet per minute. It might be the units on that. And you've got an output flow rate. So input flow rate, output flow rate, x of t, and the the water in the tank has a height of y of t. Okay, and if you look down on it, it might be circular, and so it has a cross-sectional area A. Okay, and so what we'd like to do first is model this system. This is the plant, okay, and so we may have a little float here that is connected to some electronics that give us the difference between the desired height and the actual height, right? So this signal here for the height might be converted to voltage, and then you have also a reference voltage there, and the error signal, you take, say, the difference between this electronic comparator, say, and that signal, it goes to, that error signal goes to a valve, right, which increases or decreases the flow rate, okay, in order to maintain a constant level. So this is a liquid level control system, okay, and so the plant is described by the following. Well, we want the mathematical model for it, right? And so you can say that the rate of change of volume with respect to time is equal to the input flow rate minus the output flow rate. And also, I wanted to mention that the pipe here has a certain resistance, and the resistance will be, I should say, the flow rate here, x of t, will be inversely proportional to the resistance. So you've got the pipe resistance to the flow of fluid, and it's proportional to the height. Okay, and so now we can also what we can say is that the volume is equal to A times Y. Right, Y is the height. So you've got the volume. So you've got A is a constant cross-sectional area times d and the height. I'm calling it Y. Oh, this should be Y too, right? Y. And so A dy by dt is equal to U of t minus x of t, and I can use y of t over r, so y of t, I'll just, you can just use u, right? U minus y over r. So here we have a first order linear differential equation with constant coefficients. Right? A is constant, R is constant, and so we can let's choose some convenient values just for the sake of simplicity. So let A equals R equal 1. Okay.
Is the R is that radius of the actual tank itself or the output? Or resistance? It's not like a radius. Yeah.
It's not a radius. Mm-hmm. It's just a kind of resistance to the flow of fluid.
Okay.
Through the pipe.
Got it.
So it has a certain value.
Okay.
And so we're letting it equal 1. And so now what you get is dy by dt is equal to u minus y. And simple model, right? And so what we want is this model, but what we'd like typically is a transfer function, right? We've been working in terms of transfer functions. And so we'll take the Laplace transform of this, and when you take when you find the transfer function, you assume zero initial conditions, right? So you have s times y of s is equal to u of s minus y of s, and solve for the ratio of the output, which could be the height. In other words, here we have the system, the plant, right? That is depicted there, and you have an input flow rate u of t, and you've got an output flow rate x of t. Or you could, you see, since x of t is related to y of t, you could have an output y of t. You could use one of those because they're related by a constant. Okay, so I can use this one here. Input u of t, output y of t, and that goes along with this differential, this equation here. So let's find the transfer function. The transfer function, in the Laplace domain, you have y of s, and then here you have u of s. And what we're looking for is a transfer function g of s related the output to the input. So we'll get the g of s as that ratio, right? Y of s over u of s, output over input. So you got s plus 1 times y of s equals u of s. And so y of s over u of s, this is our transfer function g of s, is simply 1 over s plus 1. Okay, so that's pretty simple. Right. And so up here then, this is the reference input, right? So this is y reference, and then we have the actual height here, and then this output here is connected to the valve, which turns off and on, and keeps the height at a certain relatively constant. And so as a control system, you might depict it like this. You have a plus, and this is y reference, and this is the actual height. and this is the G of S here, and it's a feedback control system, right? And then we have the Y here, and we're feeding back, negative feedback. Okay. So what we said is that we're interested in the frequency response of the open loop transfer function, right? So the design and analysis using the frequency frequency response, really we're talking about the frequency response of the plant, okay? And so in order to get the frequency response, we find it's called the sinusoidal transfer function. Sinusoidal transfer function is obtained by replacing S by j omega. Okay, so you've got G of j omega. And before I look at the expressions for the magnitude and phase of this sinusoidal transfer function, let's take a look at how such a transfer function might be generated. Okay, so we have a sinusoidal input, say, apply a sinusoidal signal of frequency omega to our plant, more specifically to the open loop transfer function, GH. Okay, and here, let me just call it G in the case where we have unity feedback there. And this is G of S. Okay. And in order to generate the frequency response, we apply a sinusoidal input, and we look at the sinusoidal steady state response. The steady state response. So the steady state response will be equal to, before I write that off, we replace S by j omega. So j omega is imaginary value, and g of j omega will in general be complex. And this complex quantity can be expressed in terms of its magnitude and its phase g of j omega. Okay. Another way of writing this is the magnitude of g of j omega e to the j theta of omega. And that theta of omega is identically the same as the phase of g of j omega. Okay. And now the sinusoidal steady state, y SS for steady state, output for the sinusoidal input to the transfer function, a system having transfer function g of S, is going to be equal to the magnitude of g of j omega times the cosine of omega t plus theta of omega. Okay, so what that says here is that if you apply a sinusoid of frequency omega, the output in this steady state will also be a sinusoid of the same frequency. However, its magnitude will be scaled by the magnitude of the transfer function at that same frequency, and the phase will be shifted by the phase shift of the transfer function. Okay, so this is all analytical, but this can also be done experimentally, right? In other words, you can apply a sinusoid. It might be depend if it's a mechanical system, it would be maybe a sinusoidal vibration to the system, and you look at the response of the you know, the output of the system in this steady state. And what you can do is plot. You can tabulate or plot the magnitude versus frequency. So you've got for Ayres frequency, you've got the magnitude G of J omega, and you've got the phase theta of omega. Okay, so this is a frequency response tabulation. So you can start with the low frequency, and well, it might not be zero, but small. Okay, and you increase to to the large values, that apply to the particular system that you're working with. So the frequency is increasing, and as the frequency increases, you can find the corresponding magnitude and phase for each of these frequencies here. So you have a table here. Another thing, so let's do it for this system that we have here, this open loop transfer function. The magnitude of, first of all, the G of J omega, G of J omega is equal to of 1 over 1 plus J omega. Okay, and so from this you can get the magnitude. The magnitude of the quotient is equal to the quotient of magnitudes. Okay, so the magnitude of G of J omega is equal to 1 over the square root of 1 plus, and remember, it's the magnitude of this squared. It's magnitude of that squared plus the magnitude of that squared. So that's going to give omega squared there. And then the phase expression, like this one here, is going to be the phase of the numerator minus the phase of the denominator. And so the phase G of J omega phase which is the same as theta of omega. The phase of the numerator is 0, right? It's a positive real number, right? And in other words, you've got a 1 here, and you draw a vector from the origin to that point as a phase of 0. So it's 0 minus the phase of the denominator, and the phase of the denominator is the arctangent of the imaginary over real. So this is going to be minus arctangent omega over 1. Okay, so you've got expression for the magnitude and phase. And so we can tabulate, for example, if we have zero frequency, the zero frequency, this gives 1 and this gives 0. Right? So the magnitude is 1 and the phase is 0. And we can increase, let's say that the frequency is 1. For a frequency of 1, we have 1 over square root of 2, 1 over square root of 2, which is 0.707, right? And the phase with an arctangent of 1 is just going to be minus 45 degrees. Minus 45 degrees. And as the frequency increases, this phase here becomes minus 90, right, for high frequencies. And this is getting smaller and smaller. Okay, so we can tabulate. We can also plot. Right, if you plot, for example, the magnitude here, what the magnitude might look like is just do the positive frequencies, it starts out at 1, right? Let's get it from the table, and it's going to go down, and so it's really kind of a low-pass filter, okay? And so this is the magnitude of G of J omega. And you could also plot the phase theta of omega. The phase starts at 0, and so it's 0 degrees. It starts at 0, and it's going to end up at minus 90 degrees, or if you want to express it in terms of radians, it's minus pi over 2. And so it does something like this. And this is on a linear scale of frequency, like 0. And then at 1, at the frequency of 1, we have minus pi over 4, right? And here you could do the same thing at the frequency of 1, well, and this is 0.5, and this is 0.7, so 0.707 at the frequency of 1. So these are linear plots versus omega on a linear scale, 2 and so on. So there's 1 and 2. And so now, when we talk about Bode diagrams, we are not plotting versus a linear scale. We're going to be plotting versus a logarithmic scale. And also, we will have a Bode diagram for magnitude, another Bode diagram for phase. So now what I want to start doing is talking about straight line approximations of the Bode diagrams. Not the exact Bode diagram, but the straight line approximation. And we'll get to a point where we can draw the Bode diagram almost by inspection. Okay, the straight line Bode diagram. And then, we can look at the Bode diagram as generated by the MATLAB, and we have some what's the word? We're confident that our Bode diagram as generated by MATLAB is correct because our approximation is close to it. Okay. So that's what I'm going to talk about next. But are there any questions or comments? All right. So the Bode diagram, when we talk about the Bode diagram, just like here, we've been talking about the open loop transfer function, GH. In this case, it's just G, right? And over here, we generated the open loop transfer function, which is really that's the Planck transfer function. And we haven't considered a compensator. The compensator typically would go in the forward path here, so that this would be a lead or a lag compensator here to improve the response characteristics, transient and steady-state response characteristics, using a lead or a lag type compensator or a combination lead lag. Okay. So we want to consider straight line approximations. Bodie diagrams of magnitude and phase. Alright, just like over here, we have this one transfer function that we start out with 1 over s plus 1, and when we replace s by j omega, forming the sinusoidal transfer function, that sinusoidal transfer function could be analyzed in terms of its magnitude and phase versus frequency. Tabulation here, this is magnitude versus frequency, phase versus frequency. We'll also later look at the G itself, the G of S, and we'll let S equal J omega typically, and we'll let omega go from 0 to infinity as we've done here, but we'll plot the imaginary versus real of G of J omega. So this is the G, or more generally, plotting the imaginary versus real of G of S. So this is the G of S plane here, and this is what is called the polar plot, or Nyquist diagram. Right? So we'll be talking about the Nyquist diagram as well. So this Nyquist diagram usually can be obtained from the frequency response tabulation, right? Just as the magnitude and phase expressions versus frequency can be obtained from the tabulation. And this tabulation could be obtained experimentally, right? You've got the actual system that you're trying to analyze, and you apply sinusoid to it. You look at the sinusoidal steady state response. The magnitude of the amplitude of the sinusoidal output is really just the magnitude of the sinusoidal transfer function, the magnitude, and the phase shift here. The phase shift here is just the phase of the transfer function, right, at the certain frequency that you apply of the sinusoid. Okay, so straight line approximation of the Bodie diagrams of magnitude and phase. So let's start out with some general G of S, and it's a product of factors A times B over C times D of S. Okay, and in order to go from the transfer the transfer function to the sinusoidal transfer function, you replace S by J omega, right? So we go to G of J omega that's equal to A of J omega, B, and so on. J omega. So this is just a typical transfer function. I'll give some examples in a little bit, but here's the sinusoidal transfer function. Now, each of these factors here is complex, and therefore they can be represented in terms of magnitude and phase, right? So this can be represented as some I call it M1 e to the j theta 1, M2 e to the j theta 2, and so on, M3. And you know that this can be separated into M1, M2 over M3, M4, e to the j theta 1 plus theta 2 minus theta 3 plus theta 4, right? So I'm subtracting the denominator phases, right? And so this right here then is going to be, clearly they're functions of frequency, so it's m1 of omega, m2 and so on, theta 1 of omega and so on. So this is going to be this would be the magnitude right here. Isn't this not h? This is the magnitude of g of j omega. That's magnitude, and this right here is the phase of g of j omega. Okay, and so this, instead of writing this as an angle q of omega, it's totally identically the same as you can call theta of omega. And so the g of j omega can be expressed as the magnitude of g of j omega and an angle of g of j omega, or magnitude of g of j omega at e to the j theta of omega, like that. Okay. And so let's now, instead of working with this expression up here, what we'll do is work with the log of the magnitude. Okay, because if you take the log of the product, it becomes addition, right? The log of the quotient is subtraction, and so it basically converts the the process, the arithmetic product to addition, quotient to subtraction. So we'll have, and in fact we'll take 20 times the log, and it's a log base 10 of the magnitude of g of j omega. And this is just kind of what has kind of passed down from decades. It doesn't have to be 20, but that's typically what is used. And if you do this, then this is going to be equal to 20 log base 10 of m1 plus 20 log base 10 of m2 minus. Actually, the way I can write it is plus 20 log of 1 over m3, right? That's the same as minus 20 log m3, and so that plus 20 log of 1 over m4. And so the Bode diagram, right, of magnitude is a plot of this magnitude here versus frequency on a logarithmic scale. Right, the Bode diagram of magnitude, you're plotting this versus frequency on the logarithmic scale. Equivalently, it's a plot of the summation of each of these here versus frequency on a logarithmic scale. And the straight line Bode diagram is a plot of the straight line approximation of each of these terms here. Okay, so we basically what we do is find a straight line approximation for each one. We can draw it out, okay, and then add them all up, right? So you've got 4 plots, and then you add all those plots to get the composite plot of magnitude. And as I say, we're going to find a straight line approximation for each one of these. And then we're going to do a similar thing for the phase, right? The phase, say, theta of omega. Well, here, it's already in the form of a summation or difference, right? So we don't have to, go through some kind of a log because it's not a product that we're starting out with. And so we just plot this straight line approximation for each one of these versus frequency on a logarithmic scale, and then add them up. Okay. Now, and so we'll have straight line Bode plots of magnitude and phase versus frequency on the logarithmic scale. Just like here, we have magnitude and phase on the linear scale. Oh, and about the scale itself, the logarithmic scale, I'll put two scales here. This one is frequency omega, and this one here is also, actually this one down here is the log base 10 of the frequency, and this one is just frequency there. And you can take various frequencies. Let's say omega is equal to 1. So if omega is equal to 1, then that corresponds to, if omega is equal to 1 up here, right, 1, then down here it's 0, right? It's the log of 1, base 10, right? And then if we have, let's see here, a frequency of 10, right? 10, what is the log of that? Base 10 is just 1, right? And then here, if you have 100, here it's 2. So we're going to be using this scale here, right? This is a logarithmic scale of frequency, and you can also estimate the points for 2 and 5. They basically break up the decade. This is 1 decade, from 1 to 10, a factor of 10 increase from that is 10. It breaks up the decade into approximately thirds, 1/3, 1/3, 1/3. Okay. And again, this is 2 and 50, 20 and 50, and so on. So, in other words, if you take the log of 2, the log of 2 is going to be about 0.3. We're taking the log of 2. If you take the log of 5, log of 5 is 0.69. 0.69. So you see, it's not exactly thirds. It's a 0.3. This interval here, it's a 0.39 for this interval, and it's a 0.3 over there. And similarly up here, this would be, 1.3. 1.3. This 0.3, that's 1.3. And 50 would be 1.69. Right? And you could do it for any other frequency in between. Okay. So we're going to be using this scale here. So we want to use this one. When we plot the straight line Bode diagrams of the individual terms, and then we're going to, and then we'll add all of them up to get the composite. So, let's consider the various possibilities for these factors here. Right? We could have so these are possible factors. And it could be a positive or negative constant. It could be of the form. Now, this is just the way that I like to present it. The book may present it a little bit differently, but I like, the next possible factor might be s over omega 1 raised to the n, where n, it could be plus or minus 1, plus or minus 2, and so on. If, for example, if n is equal to 1, then it's just s over omega 1. If n is equal to minus 1, it's actually omega 1 over s. Okay, so we're going to look at each of these factors in terms of their magnitude and phase. Okay, and then 3, the factor is plus or minus 1, plus or minus s over omega 1 raised to the n power. And again, n can take these values plus or minus 1 and 2. Typically, you don't find them raised to a real large power. And 4, it could be a quadratic factor where the damping ratio is between 0 and 1. So it could be a factor of the form s squared plus 2 zeta omega n s plus omega n squared. And this over omega n. And it doesn't have to be over omega n. It could be something 2 times omega n. It could be 100 times omega n. But this is kind of a standard that you can start out with. And then here it could be a plus or minus 1. It could be larger powers here, like squared, but typically just stick with these low powers. And of course, if it's plus 1, it's just this what you see. If it's minus 1, it's the reciprocal of that. Okay, so let's consider some example transfer functions. And the way that we would like to, the form we'd like to put them in when we go about finding the straight line Bode diagrams. So let's say we have this h of s is equal to 10 squared times. See, in fact, these are the forms that we'd like to put them in, right? Either as a positive or negative constant, some s over omega 1. If that appears in the transfer function, we'd like to put it into that form. And so here we have 10 squared s times s plus 10 cubed. Okay, divided by s plus 10 squared. And then we have s plus 10 to the 4th. So what we want to do is get this transfer function, the factors of this transfer function, into the form of 1 plus or minus s over something. For example, these 3 factors here could be put in that form. And then here, so let's just start factoring out. This, you see, is equal to, we have an s, we have 10 squared, and then we take a 10 cubed out. Right, if you take a 10 cubed out of that, then what you're left with is 1 plus s over 10 cubed. And that's kind of the form that we would like it in, right? So it kind of corresponds to this. Okay, and then let's see, in the denominator here, we would have, we would factor out a 10 squared here and a 10 to the 4th there. So we factor out a 10 to the 6th, right? And then you could say that this is 1 plus s, 1 plus s over 10 squared, and 1 plus s over 10 to the 4th. Okay, 10 to the 4th. So now simplifying that, this will be, see, 10 to the 5th over 10 to the 6th, so that's s over 10, right? And so it's in this form here, right? And then the rest of the factors, you've got the 1 plus s over 10 cubed, with that factor, and you've got these two factors, 1 plus s over 10 squared, and 1 plus s over 10 to the 4th. So this is the desired form, the form you'd like to get it into when you begin the process of drawing the straight line Bode diagrams of magnitude and phase. Okay, and so let's go on to and consider positive and negative constants and the Bode diagrams of magnitude and phase. Right? So we could draw a little table here. We have the factor, we have the magnitude m, we have the phase, actually the magnitude in decibels, right, which is 20 times the log of m, and we have the phase. Okay, so the factor, we're considering positive and negative factors. It could be 1 or minus 1. And so what is the magnitude? The magnitude is just 1. Right? And the magnitude in decibels is 0, right? 20 log of 1 is 0. And then the phase of a positive real number, the phase is 0. A negative real number, the phase is 180. Okay? So over here we have 0 or 180. Or you could use minus 180, please. Right? And so square root 2 or minus square root 2. You've got the square root 2, and the magnitude in decibels, 20 times the log of that, is going to be approximately 3. And the phase is either 0 or minus 180. Okay. And then you could take 1 over square.
1 times negative 1 come from?
Say that again.
On the factor part, where does the 1 times negative 1 come from?
Oh, it's not product. It's just either this or this.
Is that from like the first list on the possible factors?
Yeah, the factor that we're considering is could be a 1 or it could be a minus 1.
Did you just choose that number out of nowhere?
Sorry?
Did you just choose that number out of nowhere, or is that coming from that?
I took it just to get us started. Okay, and I picked it kind of arbitrarily, but you know, it's a convenient one for which the magnitude is 0. Okay, and so you have either 1 or minus 1. The magnitude is always 1. The phase is 0, and I'm sorry, the magnitude decibels is 0, and the phase is either. For 1, it's 0. For minus 1, it's 180. And similarly here, right? Magnitude is square root 2. Magnitude in decibels, 20 times the log of square root 2 is 3. And the phase, again, is either 0 or 180. And then if you have 1 over square root of 2, or minus 1 over square root of 2, then you have 1 over square root of 2 for the magnitude, and here you have minus 3 dB. Minus 3 dB, right? So when it's in the denominator, it goes from being positive. Numerator is positive, denominator is negative. Decibels. And then the phase is the same kind of thing, 0 or minus 180. And so you could do it for several factors, right? You could do it for 10 and minus 10. 1 over 10 and minus 1 over 10. So in one case you would get in fact we'll do it, have 2 minus 2, and it's the magnitude is 2, and the magnitude magnitude in decibels, 6 dB. Okay, and the same thing here. And 10 and minus 10 is 10, and it's going to be 20 dB, right? 20 times the log, and so on, and 1 over 10, minus 1 over 10, 1 over 10, minus 20 dB. Okay, so, and then we can plot any one of these. For example, let's plot minus 1 over square root of 2 in terms of magnitude versus frequency, on the logarithmic scale. The magnitude is going to be minus 3 dB, right? So here's the frequency scale, omega, logarithmic scale. Right? This might be 1, this 10, this 100, right? And it's going to be a constant for all frequencies, and the level is minus 3 dB. And so that's the magnitude plot here. Or that's the magnitude plot. And it's constant for all frequencies from the lowest to the highest. And the phase of this negative number is just minus 180. Right? So in terms of phase, if this is the scale, omega, then the phase is going to be minus 180, constant phase for all frequencies from zero, which you can't really depict zero frequency on the logarithmic scale. Right? This is 10, this is 1, this is 0.1, this is 0.01, this is 0.001, and so on. Okay, so there's no approximation. They're already straight lines. So there's no approximation here. So now let's consider the next factor. The next factor is this one here. Okay, so S over omega 1 raised to the n. And I'm going to replace S by j omega. Right? So you have j omega over omega 1 raised to the n. And if you depict this in the complex plane, in other words, imaginary versus real, this is depicted as a vector along the positive imaginary axis. And this point here is omega over omega 1, right? And so the magnitude of that vector, call it m1, is just equal to omega over omega 1. And the phase is 90 degrees, right? So m1 and theta 1 equals 90 degrees. And so this is equal to, inside the parentheses, I'll just put the polar coordinate representation. So you've got m1 e to the j theta 1, and that's raised to the n power. Right, and so this is just equal to m1 raised to the n times e to the j n theta. And so this is the composite magnitude m, and the phase theta. And in other words, this in terms of magnitude and phase. So the magnitude in decibels is 20 times the log of n, and m1 is omega over omega 1. So you've got 20 times the log of omega over omega 1 and it's raised to the n, right? And so this is equal to 20n log this base 10 omega over omega 1. So that's the magnitude in decibels. And theta, well, this is theta 1, right? Yeah, n theta 1 is our theta. So theta is equal to 90n, because theta 1 is 90 degrees. Okay? And so now we can go ahead and tabulate and then plot. Okay? So we have frequency omega, we have the magnitude in decibels, and we have the phase. So we start out with some low frequencies, say 0.1 omega 1, and then go to 1 omega 1, and then 2 omega 1, and 10 omega 1, and 20 omega 1. Right, so we're just increasing frequency. It's for some unspecified frequency omega 1. Okay. We find the magnitude and phase in each case. Of course, the phase is going to be 90n all the way down. And this n here can be positive or negative, and so the phase can be either plus or minus 90. Okay, so in terms of the magnitude, if you substitute 0.1 omega 1 into this expression here, you'll get minus 20 n, right? And so on down, with a 1 omega 1, you get 0, 6 n, 20 n, and 26 n. Okay, notice that in going from 0.1 omega 1 to 1, that's 1 times omega 1, that's a 1 decade change in frequency, a factor of 10, right? If you go from 1 omega 1 to 2 omega 1, that's what's called an octave, a doubling in frequency, okay? And here, again, this is an octave there. Okay, now let's plot this, and it looks like this. What we have is, let this be 0 dB, and let this be 0.1 omega 1, and then this omega 1, and then the 10 omega 1. See, it's on a logarithmic scale, right? And this is omega, right? And so when omega is equal to 0.1, we have minus 20. So let this be 20n, right? And this is about 10, and this is about 6n. And then we have underneath here as well, this is minus 20n and minus 10. So minus 6 is roughly here. Okay, so we have minus 20n at that frequency. So we have that point there. And then we have at the frequency omega 1, it goes at that point. And then at the 2 omega 1, remembering that the 2 and 5 roughly break up the decade into thirds. So at this point, we have about 610 dB. And then at 10 omega 1, we have 20n. So 10 omega 1, we have that. And so then we just join these points. And so what you see is that it's a straight line. Again, there's no approximation to be made here. Okay. And what we're going to point out here is the slope. What is the slope of this line? And it's so many dB per decade. What is the slope? It's 20, right? And in other words, if you go from here to there, that's 1 decade. And the change in magnitude, right, you go from minus 20 to 0. So it's an increase of 20 dB for that decade. And since it's this constant slope, this line here has a slope of 20 n dB per decade. It's 20 n, right? Because it's kind of for the general case here. If n is equal to 1, then it's just 20 dB per decade. And notice also, if n is negative, it's going to be minus minus 1. It's going to be minus 20 dB per decade. And in other words, it's going to be going down the other way. Okay, so the phase is constant at 90 n, right? In other words, for a given value of n, if n is equal to 1, for example, you plot, if this is 0 degrees, the phase will be 90, period, or be 90, if n is equal to 1, for all frequencies, right? So this is the logarithmic scale, and this is the constant phase. So this is something then that you can if you have a constant, you can, by inspection, you can plot the magnitude and phase. Okay, if you have a factor of this form, s over omega 1 raised to a power, you can plot by inspection, right? If you know what omega 1 is, for example, if omega 1 is equal to 2 and n is equal to 1, this is going to be 2, this is going to be 0.2, this is going to be 20, right? And the slope is going to be 20 dB per decade. Okay? So now, any questions? Let's go on to the next factor, right? Let's see, for example, like here, we have s over 10. This is the n value is 1 because it's raised to the first power, and omega 1 is 10. So that can be easily plotted, a straight line Bode plot of that factor. So then what we're going to consider next is a factor of this one, 1 plus s over omega 1 raised to the n. So, I mean, later we'll consider plus or minus here, plus or minus there. But we go through a similar kind of analysis where we replace s by j omega. So we have 1 plus j omega over omega 1 raised to the n. And then we take a look at the inside here and depict it in the complex plane. So we have the imaginary component is omega j omega over omega 1, and the real component is 1. Right, so we have a vector here. Notice that this vector, when omega is 0, there's 0 imaginary component, and so it's just pointing along the positive real axis. Okay, as omega increases, the phase increases correspondingly, and in the limit, when omega is very, very large, the phase approaches what? 90 degrees. Yeah. So let's find we call this the magnitude m1, and this the phase theta 1. And so the magnitude m1 by the Pythagorean theorem is just equal to 1 plus omega over omega 1 squared. Just take the square root of that. Right? And the phase theta 1 is equal to, the phase theta 1 is the arctangent of that over that. Right? Or arctangent of omega over omega 1 divided by 1. Okay. And so we have magnitude phase. Now we can go on with this here. So this is equal to m1 e to the j theta 1, and that's all raised to the n power, right? And so we can express that as m1 to the n e to the j n theta 1. Okay? And so this is the composite magnitude, call that m, and this is the composite phase, call that theta. Right? So m is equal to 1 plus omega over omega 1 squared, and here what we have is the 1/2 power, it's also n over 2, and theta will be equal to n arctangent of omega over omega 1. And then we express this magnitude in decibels. So m in decibels is equal to 20 times the log of m, and that's going to be equal to, with m here, that becomes n over 2 times 20, or 10 n log of 1 plus omega over omega 1 quantity squared. So, and here we have the magnitude in decibels and phase. Okay. So what we're going to do is generate another table and draw the straight line approximation from that table. Now, actually, we're going to draw the exact plot. But let's start the table out. We've got omega. We've got m, we've got magnitude in decibels, and we've got theta. So let's start out at 0, and go to 0.1 omega 1, and then 0.5 omega 1. We have omega 1 itself, 2 omega 1, 10 omega 1, and 100 omega 1, and then the frequency approaching infinity. Right? And so we have the corresponding magnitude, and so and put in the magnitude here. It's at 0 is 1, at the 0.1 it's still very close to 1. Okay. And 0.5 it's 1.11. Okay, and then at omega 1 it's the square root of 2 raised to the n. Okay, and then we get the square root of 5 raised to the n. We've got 10.05 raised to the n. We've got 100 raised to the n. And when the frequency goes to infinity, the magnitude goes to infinity as well. Now here what we're going to do is plot the magnitude in decibels. So it's 0, 20 times the log of 1. It's still very close to 0 here for 0.1, approximately 0, and then it's 0.97 n. It's approximately 3 n dB, 3n. And then we have 6.99 n, and then 20.04 n, and 40 n, and then it's going to infinity. All right, so we have the magnitude in decibels, and then the phase here starts out at 0, 5.7 n, and it goes to 26.6 n, 45 n, 63.4 n, 84.3 n, 89.4 n, and it's approaching, as you can see, 90 n. Okay, so the next thing we want to do here is plot the magnitude and phase versus frequency on a logarithmic scale. And what I'm going to do, since I messed that up, but I'm just going to plot the straight line approximations. And so these straight line approximations look like this. We start at 0 dB, that's magnitude, and then this is 20 n. And the straight line approximation consists of a straight line along the axis here up until we get to omega 1, and then it starts increasing at the rate of 20 n dB per decade. Okay. That is a straight line approximation. If you plot the actual points, what you would find is that they go something like this. Okay, so the actual points are pretty close to the straight. I should say the straight line is pretty close to the actual points to the actual curve. The maximum error occurs here at this circle break frequency. If you plot the phase, it will look like this in terms of the straight line approximation. You let this be 0.1 omega 1, and this be 10 omega 1. Straight line approximation of phase looks like this. Again, 0.1 omega 1. It's going to be 0, because this is 0 degrees. It's going to be up here. 45. It's going to be 90 n. Okay, and then let this be omega 1, and this over here 10 omega 1. And so it's going to look like this. It's going to, this is 45 n. It's going to go through a point here and a point here. This is a straight line. And then it will flatten out. If you plotted the actual voted, sorry.
Just after you finish. Sorry, that's it. I was gonna ask, is what you're showing on the top? I know the bottom's the phase, but is this like a high pass filter? Then you said.
This is basically still a low pass filter.
Is it?
Right. For example, if n is -1, it's going to be breaking downward.
Okay. All right.
And so this has a slope of 45 n dB degrees per decade. That's the slope. If you plotted the exact plot, it would look like something like this. Okay, you just use that tabulation.
Okay. Yeah.
Okay. We're going to start next time with these straight line Bode diagrams that have these standard factors with some examples.
Okay.